Hardy-Cross method conducts an iterative analysis that solves for a looping pipe network problem. Considering a looping network with one inlet supplying 900 liters per second of water and 5 outlets, the overall dimension of network is 65 meters by 120 meters. The water demand for the outlet nodes varies from 100 to 300 liters per second. 500 mm ductile iron pipe is used. The Hazen Williams coefficient for DI pipe is taken as 100. First, we want to determine the expression for head loss through every stretch of pipe based on Hazen Williams head loss equation. The expression will be in terms of flow rate Q for the ease of implementation during the iterative process. Once we obtain the expression for head loss, we will be determining the resistance against the change in flow, R, by differentiating the head loss expression with respect to Q. Let's make our first assumption on the flow in pipes. The assumption needs to comply with the continuity of flow, where the amount of water entering a node equals to the amount of water going out from it. Say, we assume the flow occurs in all pipes except BE and CB. Flow through pipe AB is 400 liters per second, and it is reduced to 200 liters per second in pipe BC. For pipe AF, FE, and EE, the flows are 500, 400, and 100 liters per second respectively. Based on the configuration of pipelines, we can establish two flow loops, namely ABEF and BCDE. Next, we set our sign convention for flow direction for loop. By isolating each loop, we set the flow direction as positive if water is flowing in counterclockwise within the loop. Positive flow direction for all pipes is determined and it is referred throughout the analysis. To make the analysis easier, we construct a table for each loop to present the calculation in organized manner. Let's go with the first iteration based on the assumed flow. The flow in pipe FA, EF, and DE are in negative direction, and flow in pipe AB and BC are in positive direction. The calculation of head loss in pipe needs to take the direction into account. Meanwhile, the calculation of R does not require us to do so. Flow rate correction is calculated by dividing summation of head loss with the summation of R. The flow rate is then corrected by subtracting the correction from the assumed flow rate. The resultant flow rate is then used as the analysis basis for subsequent iteration. For pipe BE, which involves in both loops, the flow rate is corrected in the same way, except we need to add the correction from another loop. The procedure is continued until convergence is achieved, where the flow rate correction becomes negligible. The result shows that this method can always lead us to the correct solution regardless the accuracy of our first assumption. Nonetheless, a first guess that nowhere near the actual flow condition requires more iteration to converge. Typically, a complicated network requires great effort to solve. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.